Can you see my writing?
Yeah.
Okay, great. Our lesson today is about vectors. And vectors are simply arrows, basically, that show the direction of something like a force, like a push or a pull, or the direction of something's motion or their velocity, like the speed. And so you're going to draw vectors like this. There'll be some of them like this, and some of them this way, and some of them this way. And what we can do is we can add the vectors to sum. And the weird thing about vectors, you know how in math class you'll have like 5 plus 7 equals 12?
Yeah.
And that's easy enough, right? But with vector addition, you're going to use trigonometry to add vectors. For example, this is your 1, and this is your 2. And it'd be like, let's say you were in walking outside in a park, and first you walked north 10 meters, and then you walked east by 13 meters, right? For you to add two different distances or different displacements, and if you're going to have these two distances and they're not in the same direction, the only way you can add them, since they're not in the same direction, is by using trigonometry. Now, it would be easy enough if this were the 10 meters and if this were 13 meters and you were in the same direction, then you could just say, oh, that's easy. The sum is 23 meters north, right? Because they're in the same direction. But in the same direction, you have to use trigonometry, and here's how you do it. The sum is actually, and you always go from the very beginning. So the sum, there's a special word for the sum, and that's called the resultant. So you're going to say, find the resultant of these vectors. So that you can think of the word result, like resultant. So this resultant is going to be, in this case, the vector that goes from the very beginning to the end. And I'll send you this recording so you see all of this again. So the very beginning to the very end. I like to call it the shortcut.
Okay.
Now, some students they're very, very tempted to look at this like vector 1 and vector 2, and they're very tempted to say, oh, the resultant is this, and they get back to the beginning. But not right, because that's not the shortcut, is it? Like if you did that walk in the park with 1 and then 2, is the green arrow the shortcut?
I guess not.
It's taking you back to the beginning. So the resultant does not take you back to the beginning.
That's displacement almost. Or kind of, no.
Yeah, well, that's like how would you get back home? But in this case, I'm rid of this, and I'm going to tell you that the resultant is actually from the very beginning to the very end, and so you want to draw it shortcut. Yes, it's backwards. So all I'm saying is a lot of students try to draw the resultant backward, but it's the correct way to get the shortcut from the beginning to the end. Many, many triangles, in most word problems, the shortcut is usually the hypotenuse. Not always, but usually the hypotenuse of the right triangle. Not always, so be careful. You can add vectors. It doesn't have to be just 2 vectors. You could up adding like 16 vectors, and they might give you a problem like that. But let's add these. Just go. Let's say she gives you this vector and that vector, and then this little tiny one. Okay. Usually a lab with my students where we have these vectors which are actually arrows cut out of paper, and we show them, and we have the students like lay them on the floor, or maybe they have like Velcro on the back, and we can put them up on a felt board. But if you shuffle them and you add them in all different order, like let's say you did 4, 3, 2, you did 2, 3, 4, and you just added them in all different orders, it turns out actually to be the same exact sum, the same exact resultant. So it doesn't matter. It's really weird, but it doesn't matter what order you add them in. So we could do when you add them, what you want to do is you want what's called the tip-tail method. So we call this tip tail. What that means is where the first vector ends is where the next vector is going to begin. So I'll show you how to do that really quick. We're going to do the tip to tail method with these 4 vectors right here. We'll go first vector. Where that first vector ends, that's where we start the second vector, and we go boom, boom, boom. There's the second one, right? I forgot to tell you that you want to make the length exactly the way they show you. I'll tell you something about the length. Longer vectors, greater forces or velocities, or longer distances, for example, right? So, for example, this might be 10 meters per second. This one might be 50 meters per second. So you have to draw the arrow proportional to the number it represents, like the speed or the distance. So you not do like here's 10 meters, and then you wouldn't do like 10 meters and have them be 2 different lengths. And you also wouldn't do like, okay, 10 meters here and then 100 meters like that.
All right.
So you got to make them proportional. And the bigger arrow just means a greater force and a greater distance, a greater velocity, whatever the problem is talking about. You probably already know this, but vectors are quantities that always have direction.
Okay.
So really, I'll come back to this page in just a second, but I'll say this, that vectors have direction. So let's talk about some things of direction. Forces, right? If you're going to push or pull something, don't you that we push or pull with a certain direction?
Yeah.
Okay. Velocity. Velocity means movement, like a speed. It's speed plus direction. So when you say velocity, you might say 25 miles per hour north or west or south or something like that. So it always has direction when it's velocity. Or you could say displacement, because you're moving, certainly has a direction. You might have moved up or down or east or west or left or right, okay? So that would be your movement in a certain direction. Now, things that are not vectors are called scalars, and scalars do not have direction. Teacher might ask you, and this would be like a really small question on a test, but she might say, oh, is this a scalar or a vector? And then she'd give you something like, let me give you an example, time. If you said 2:56 p.m., that does not have a direction like north, south, east, or west. Or you're like money, if you said I have $5.50, that doesn't have a direction. So there's plenty of quantities, there are plenty of number amounts, things. And so speed is different from velocity because speed is just how fast you're going without telling the direction. So there are lots of, so you could say like with speed, you could say 50 miles per hour and don't say the direction. And so things, and I better quiet here and say without telling the direction. That means you've just told the speed, not the velocity. So, and see, there's some things that are vectors and some things that are scalars. So we're adding these vectors. We want to make sure they're the correct length. You're not allowed to change the lengths as you're copying them. You try to keep them the same. And so now add the next two. So I added number 1 and 2. Now I'm going to add number 3. And remember where the second one ended, that's where I start the third one. So I'm going to go this way.
Wait, why are we going in a triangle?
You know what? We're just adding whatever direction they went. Do you see how the first one went to the right? So the first, I'll use yellow to highlight. See if you can see the yellow. Do you see yellow?
I see it.
Okay. The first one went to the right. I drew it to the right. wherever that one ended, I started the second one. The second one went up, and so it's like that. The third one goes backwards and down. And even though it's making a weird shape, I'm going to make it go backwards and down. And notice that the third one starts wherever the second one ends. That's the tip-to-tail method.
Okay.
And then the fourth one, what color are we using? A blue? The fourth one,
yeah.
the fourth one comes down just a tiny bit. So don't make it long. Like, don't make the fourth one really long. And you can't decide, oh, I want it to reach the first arrow all the way, because it doesn't, because it's a really tiny little one.
Yeah.
And so I made the fourth one come down a little bit. So the sum is going to be a weird thing, but I'm going to draw the sum made a bright orange. So the sum is going to be, it's called the resultant, and that's going to be the shortcut from the beginning to end. Make sure you start at the beginning and go to the end. So here's the beginning, and here's the end, and I'm just going to draw an arrow like a shortcut. The arrow goes up and to the right from the beginning to the end. Do you see how that's a shortcut?
Yeah.
So it's weird the way I drew it. I was randomly picking arrows, and I probably could have picked a better pattern that was easier to recognize. But we can practice it again. You can actually add these in any order. Like if we started with the fourth one and went backwards, we'd get the same result. So let's quickly try something where I say, all right, this vector and vector and vector and this vector. And maybe we'll make this one a bit longer. Okay, let's say these four have to be added. So I'm just one more example. We're going to start with the first one just because that's logical, but it doesn't matter. You could start with the third one just because it doesn't matter. The third one, and where the third ends, I'll do maybe the fourth one. Now I can do the second one. It doesn't matter what order. I feel like the second one I did too long, but maybe I could make the original one a little longer so it matches. And the first one I'll add, and where the third one ends is where I start the first one. So I added all four. Now the resultant I'm going to do it in sort of a green color. And so the resultant is going to go from the very beginning to the very end. Arrow. And so we label the resultant as R, and that's the sum. That's how you add vector. And the reason it gets interesting is because you're going to end up with some forces, like let's say you're flying a plane. The plane has the engine, and let's say the plane wants to go forward. You know, like the plane is trying to go this way, but then there's wind, and the wind keeps pushing the plane this way. And this is the wind, and this is the engine of the plane. And you add in the wind's force and the plane's engine is by doing vector addition. So the airplane is going to end up flying off course by this much. It's a result of the airplane's pathway. So what they do is they do vector addition when they're flying planes, and they get the wind speed. They calculate the wind speed and the wind direction, and before they take off, they sort of figure out how the wind's going to push them. And so they compensate, and they'll do on purpose is they'll purposely fly the plane off course like that, so that when the wind pushes the plane like this, the plane's up going where it wanted to go in the first place. So they calculate this. This is why it's really important to understand vector addition. There are all kinds of forces at work in nature, and boats do this also because there's currents in the water, and the current might be pushing the boat one way or the other. So they have to be able to calculate, well, if the current's pushing us west and we want to go north, then maybe we could travel northeast, and then, we'll compensate for the current pushing us west. And so they do that on purpose. So your trigonometry skills, do you remember with sine, cosine, and tangent?
Yeah, I remember them.
Oh, great. So sine, opposite over hypotenuse, and cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. And this little symbol right here, we should say sine of theta is what I should be saying. That is a symbol for the angle. So that would be theta. So when you use the sine, cosine, and tangent, you really get to use these simple equations showing right angles, right triangles, I should say. So doing a right triangle, obviously, let's say I'm trying to draw one here. Let's say we've got this is the right angle, and then if this is A, B, and C, and let's say guy is theta, and let's say guy over here is beta, a different symbol for the angle. Let's say beta and theta. So we could practice just a minute, unless you feel really, really strong with sine, cosine, and tangent. How strong do you feel?
I mean, I'm not, great, but I totally understand the concepts.
Okay, just write them out really quick. So we'll do one or two examples. So since theta is opposite over hypotenuse, so on this triangle, where with theta, what's the opposite side? The side that's opposite theta?
A.
Good. So it's A over
hypotenuse, which is C.
C. Perfect. So in your calculator, you would put the angle, like let's say they gave you example, if the angle is 37 degrees, do sine of 37 equals A over C, and you'd probably be given either A or C, and you just plug in, and then you'd have just like one unknown. But your calculator will tell you what sine of 37 is. And then figure out, if they give you C, you can figure out A, or if they give you A, you can figure out C. Well, let's try one more. Let's do tangent of beta. So tangent of beta, and tangent is going to be opposite over adjacent. And what's of beta? What's the opposite side to beta?
B.
Good. B is the opposite of beta. So tangent of beta would be B over what? What's the adjacent side?
Oh, wouldn't it be A over B?
B or A. Let's look at the triangle and see. He's beta.
Yeah.
Yeah, we're doing beta. I purposely did the other one.
Oh, sorry.
That's okay. So the opposite is B. Adjacent. Yeah, here's the adjacent, because the adjacent one is always going to be sort of like part of the angle. Side, not the hypotenuse side of the angle, but the side of the angle is the adjacent. And so tangent of beta is going to be B over A. And angles, you can use all kinds of Greek letters, like, alpha, beta, gamma, all different Greek letters for these angles. But theta is just the Greek letter, I think, for T. So that's a little refresher. And then we'll get into inverse tangent and inverse sine and inverse cosine in a minute. Now, you're never going to plug in, when you do sine, cosine, and tangent, you're never going to plug in the 90 degrees, because the 90 degrees is never going to be the angle you use for sine, cosine, and tangent. I think most people know that, but I'm just saying it in case people don't know. You're going to use one of the other two angles that they give you.
Yeah.
Okay, now check this out. Let's talk about converting word problems into drawings. So she's going to say things like the lawnmower handle angle. It's too messy, tell me. 28 degrees with horizontal. And the horizontal would be what? In the case of a lawnmower, what part of that picture is the horizontal with a lawnmower problem?
It would, wait, is this in my book or is this just?
No, sorry, I'm just making it up.
Oh, so it'd be like the base?
Yeah, like maybe the ground?
Yeah.
So they word it in a way that makes you go, wait, what? The horizontal on a lawnmower? Like you've never heard of the horizontal on a lawnmower. But they're trying to get you to convert scientific words into real life situations. And so in your brain, you're supposed to think, oh, the horizontal is probably the ground.
Okay.
Okay? And then the vertical is going to be, we'll do a vertical problem in just a second. So the lawnmower makes an angle of 28 with the horizontal. Then you draw the picture, and for every problem, I want you to draw the picture. So it doesn't matter if you're good at drawing the actual lawnmower, but let's say this is the handle to the lawnmower. And so it makes an angle of 28 with the horizontal. So you're going to basically say, here's the ground, and here's the handle to the lawnmower, and here's the 28-degree angle that the handle makes with the horizontal. You can go ahead if you want and draw the lawnmower and draw the handle like that and do your angle up here with the 28 right here. Okay. You're basically getting the same triangle. So then she's going to something like, if Johnny puts, have you done forces yet?
No.
Okay, I'm going to just use forces because it's not hard. If Johnny pushes with a force of 25 newtons on the handle, what is magnitude? They love to use, in science books, love to say what is the magnitude. And it's so corny to me because all it means is what's the amount or what's the number part of the answer. So, yeah, they make it sound so hard. What is the magnitude? But magnitude just means, find the answer, find the number, calculate the number part of the answer. So magnitude is amount. What is the magnitude of his vertical force on the handle? See what I mean by this. If Johnny is pushing down on this handle, and this might not be as hard as the problem she's giving you right now, but it's going to get this hard pretty quick. If Johnny's pushing down on this handle, do you agree that he's pushing sort of down and forward both? Yes. Okay, good. What you do is it's called vector resolution. You're resolving the event into its components. So sometimes in these problems, if given a vector at an angle, like one that we just were given, a lawnmower, you need to resolve it. And resolve a problem, you sort of break it down. Yeah. Okay, when you resolve a vector, you break it down. So you break it down. You fit it into the horizontal and the components. And the components just mean the parts. Like you have the components to your stereo system, it just means the parts of your stereo system. Okay. So components are going to be, check this out, if you look up the lawnmower, which is not really looking like a lawnmower, but sort of is, we're going to say that this is a vertical component right here, the blue. So the vertical force, call it like FV for vertical force. And it's got this horizontal component, which we're going to call FH for the horizontal force. So he's pulling on that handle. He's actually pushing down and over. Down and forward, I should say. Okay. Okay, it's making sense? Yeah. Okay, good. So when you got a vector at an angle, you can break it down into the two components and you make a right triangle. Now, your teacher's not going to say, oh, to solve this problem, you'll need to make a right triangle. But I hereby give you permission for the rest of the year to make right triangles everywhere you think you need a right triangle. Whenever you got a force or a displacement, like let's say you've got a car that's going at an angle or you've got a force at an angle, all year long you're going to be making right triangles and breaking those vectors down into, you're basically going to be given the hypotenuse and you're breaking it down to get the two parts of the other two parts of that triangle, the vertical and the horizontal. That'll be happening all year long. So what we can do, if she did give you the force, and in this problem they did, they said 25 newtons, and the 25 newtons was what he pushed on the handle with. 25 newtons here, so know that it's on the handle. There, you put the 25 on the handle. And I didn't tell you this, but N stands for newtons, like Sir Isaac Newton.
Okay.
And that's the unit for force. So soon you'll be doing forces whenever you do the chapter that says Newton's laws. There'll be three major laws for Sir Isaac Newton that he came up with, and they're all about forces. And so the vectors, they introduce you first to the vectors, like how are you going to draw these forces, and then they do the chapter where it's like, okay, how are we going to, now we're going to use the vectors, and we're actually going to talk about real forces. So now you see how this is going to be used. I'm going to turn the page, and it's just sort of like a setup that I just showed you with the lawnmower. That's going to be an example problem that we're going to be doing. But I'm going to do a real problem. You said there was something about a pyramid, and so I'll draw that problem real quick.
All right.
Problem. The one that you read me, it said that there was a pyramid in Egypt or someplace, and what happened is the archaeologist, and maybe I'll draw a little archaeologist here, they climb the pyramid and go up to the top, and according to what you told me, I believe you said that it's like 136 meters high, so I'm going to put 136 right here for how it is. And the pyramid, how wide is it? Did you say 115?
Yeah.
Do you think that that's one side, or do you think that's from like a diagonal? Do they wide or?
No, it says wide.
It is wide. Okay, so let's say that this is 115, which is going to be one of the sides, because if it's 115 wide, then that means one of the sides is 115 meters.
Okay.
Okay, so do you see that as the archaeologist climbs up, they're climbing up the hypotenuse?
Yes.
Okay, so they're asking us to figure out how far the archaeologist had to climb, or what was the displacement, really. And in your book, they use delta x for displacement. And in some books, they use d. And that's basically just asking how far did the archaeologist go. In this problem, the displacement is the hypotenuse. Not always, but in this problem, so we're going to find the hypotenuse. The good thing with this is they gave us both sides of the right triangle. So we just
can use Pythagorean.
Exactly, which is one of everybody's favorites. So let's do a squared plus b squared equals c squared. And can I have a calculator?
Yes. So the first 136 squared is wait, that's kind of high.
Do the whole thing and we'll get C. I'll grab my calculator too, which I put on the table over here. Did you 78? Okay. Round it to three significant digits, and I'm going to say that the displacement or the distance that the archaeologist went, 178 meters, and don't forget your units. So that's the answer. Now, sometimes they'll ask you also for the direction. Okay, so if ask for the angle, this problem would ask for the angle?
Well, you probably have to know the incline in which the hiker went.
Okay, good. So the angle there, let's say that that's unknown. Most of these problems, they give you the angle and you have to figure out one of the sides. But it's a problem where, they gave us the sides and we don't know the angle. So it's just a little bit trickier, but what it is you do inverse tangent, inverse sine, inverse cosine. So I'm going to take tangent just because we are opposite in the adjacent. So I made tangent of theta, but you could also use sine, cosine. We know all three sides now because we know that this one is 178. So you could use sine, cosine, or tangent. But tangent of theta we know is opposite over adjacent. And so we know that tangent of theta in this problem is 136 over 115 because 136 is opposite and 115 is adjacent. There we've got the opposite side and we have the adjacent side. I'm just going to do 136 over 115 really quick.
I got 1.2.
Okay, great. And I'm going to leave 3 significant digits and do 1.18. Does that sound good?
Okay. Yeah.
Okay. So let's say tangent of theta is 0.18, and there's no units on that. Okay, we know the tangent of the angle, but we don't know the angle. That's when you do this. You see inverse tangent 0.18 equals theta. So switch sides, and you do inverse tangent. So tangent of the answer equals the angle. So you push function tangent to get the inverse tangent. And
0.867.
Are you in degrees, radians? Can you check the mode on your calculator? Can you push the mode button?
Yeah, I agree. I'm in radian mode.
Radians? Okay, great. For this problem, you need to be in degrees. So can you switch it to degrees and work the problem again? In degrees and not radians.
I got 49.7.
Yeah, and after the 7, what'd you get after the 7?
2013693.
Okay, so I left the 1.1826, the whole number, in my calculator, and I ended up with 49.78. So go with 49.78, which is like 49.8. So theta turned out to be 49.8 degrees, and you use the mode button on your calculator to get into degrees in case you're not in degrees. And so the full answer would be 1.8 meters at an angle of 49.8 degrees from the horizontal or from the ground.
Okay.
You could say the angle is from the ground. So you want to say in words how the angle is. So because here's what's important. With triangle, and say the triangle looks like this, and let's say that this is obviously 90, but let's say this is 20 here or 22. What would the other one be if it's 180? 168?
Yeah.
Okay, 2268, right? Now, it matters. Let's say that you're throwing something like a football and it's landing at this angle, right? Now, you could say, you could say 22 degrees for the horizontal, or what would be the same exact answer to say 68 degrees from the vertical?
Yeah, because it's the same. It's relative to the same thing.
Exactly. It's the same exact hypothesis. It's the same exact vector. So you really could use either angle in your answer, and they would both be right. 20 from the horizontal, 68 degrees from the vertical. you're going to get into east of north and south of west and different things like that. I want you to get into that right now. Can you tell me another problem or another point that was in? We've got vector addition. I think it'd give you an easy problem where we add two vectors and we do sort of get the hypotenuse and get the angle again. So let me do a new page. And if you're okay with that, unless you've got something really important that you think we should do next.
No, I can do whatever.
Okay. So on this next problem, if I told you that, oh, this is good. Okay. This is good. If a boat travels at 10 meters per second north, a current flows 3 meters per second east, then what's the boat's resultant velocity? In other words, the current is making him go off track. He wanted to go 10 meters per second north, but that current pushes him 3 meters per second east. And in travels, that sounds like that's a resultant. We could say if the boat heads meters per second north, like that's where he's heading. He's hoping to go north, but the current pushes.
Oh, I see what you're saying.
That he intended one thing, and the current messed him up. We can do it. We say we can draw a 10 meters per second north like this. So I'm just going to do the 10. So when I draw the triangles, I don't always show the units when I'm drawing the triangles, but it's fine if you want to. And then with the to-tail method, first vector ended, that's where you start the second vector. Now understand that the in the word is pushing on the whole boat, but when you draw the vectors, you're just going to make it look like it's pushing on the tip of that arrow. You know, like because you're adding tip to tail method. So the current is going to be 3. Does that?
Yeah.
And so now the resultant velocity of where the boat actually ends up going is the shortcut, or from the beginning to the end, and there's the R. So calculate it, shall we?
So it'd just be square root of 13, right?
Yeah, to square the 10 and square the 3. So maybe square root of 109. I'm not sure. 100 square, 10 squared
plus 3 squared 9. 10.44.
Yeah, 10.44. So the resultant velocity is 10.44 meters per second. So it didn't slow him down much. Not really headed on track. We need a direction now. They might ask you for the magnitude and the direction. And that's textbook's fancy way of saying, look, we want this. We want how fast he's going. That's the magnitude. You got the lead, right? But direction is going to be the angle. So when they find the magnitude and the direction, they do want to know the 10.44, but they should find the angle. Yeah, they need the angle also.
Oh, they need the angle? Why would they not? Why don't you just say like northeast or something like
that?
Good,
very good. Because in physics, you know the exact direction, not just northeast. Yeah, they want to say no. You got to calculate it and actually get a number for the angle.
Okay.
So do you remember this inverse thing we did, like inverse tangent and inverse all that?
Yeah.
Okay. We know that the R is 10.44. I usually like to use the original numbers that were given just because I know those are accurate instead of going with what I calculated. So I'm going to use the 10 and the 3, and I'm going to say opposite over adjacent. So I'm going to do, again, tangent of theta equals opposite over adjacent. So tangent of theta equals 0.333, which is inverse tangent of 0.333 equals theta. All right, so let's try that.
Let me put that in. So negative tangent of 0.333. I got 0.41.
Okay, great. So the angle is 18.4 degrees. So over here, and you say at 18.4 degrees, and now I'm going to go ahead and teach you the north of west and stuff like that. So, but now we've satisfied the book. When the book said magnitude and direction, now we have the direction. We did both magnitude and the direction. So we're good. But I'm going to use something with this north, south, east, and west, okay? Here we have, obviously, north, south, east, west, okay? If you find the angle, like, let's say you find this one right in here, okay? Like we just did. That's similar to what we just did, right? Okay. Right here, it went east of north.
Okay.
East of north. It's from the north direction, it went to the east side of north. Okay? So this one is 18.4 degrees east of north. Now that's different from north of east, because check this out. This one over here, I'll label it beta. This one is north of east because it went to the north side of east. So it would be 90 minus theta. You know, those two together equal 90.
Yeah.
And so it's not the same to say 8.4 east of north and 18.4 north of east.
Okay.
You know what I'm saying? So they're different.
Yeah, because it's not the same angle. It's
not the same angle, no. One is 90 degrees, you know, one equals the other. So let me quiz you and see if you can get some on this compass-looking thing that I drew. Okay? So what's this angle in here?
What it'll be, like 90, or it would be...
Instead of a number, just do words like east, south, north, and west. It would be something.
So south of east.
Perfect. This one is south of east. It went to the south side of east. It's this one in here.
East of south.
Good. East of south. We're going to finish it out, if you don't mind, just for practice.
Okay. So the next one would be west of south.
Good. West of south. And what would this one be?
South of west.
South of west. Good. And then we get maybe an orange. I hardly ever use orange, but with this one right here.
Northwest.
Good. North of west. One.
And west of north.
Good. You get it. So now you know, like, no matter what angle you draw in a problem, like you've got another problem and it goes, you this, and then you drew this, and then, you know, you made a right triangle. Make sure you make right triangles. Did you notice how if I connected the end of those two, it wouldn't be a right triangle?
Yeah.
Make sure you make right triangles. When I give you permission for the rest of the year to make triangles, I'm saying you've got permission to make sure they're right triangles. If the ends of your angles, like let's say you draw one of them too long, and it's like, oh shoot, I drew this one too long, and now when I connect it, well, it actually did turn out to be a right triangle, but, you know, sometimes you draw it, and it's like, oh, it doesn't turn out to look like it's a right triangle or something like that. Just don't worry about how long you drew the arrows. Just make sure that you end with a right triangle.
Okay.
Okay, now, without looking over at the compass on the right, try not to look at the compass. If you just had this drawing right here, and you had to answer the question, is they south of north or east of west, or what is it?
West of south.
Very nice. So this right here is west of south. It went to the west side of south because this south basically went west of south. You understand how you do those. A lot of times, instead of north, south, east, and west, you'll be using horizontal and vertical, or to the left or to the right, or up and down. You know, there's all kinds of ways you might phrase it. However they phrase it in the problem, like in the actual wording of the problem, you're going to phrase it that way. If they say from the vertical in the word problem, you're going to use from the vertical, from the horizontal. If they say east, south, northwest in the word problem, that's the language you're going to use in your answer. You know, if they say up, down, left, right in the word problem, you're going to use up, down, left, right in your answer. Okay. So tell me another type of problem that they give you.
All right. So I'm going to do add vectors algebraically. Like, they give us a D1, a D2.
Sure.
Okay, so the things are 27.0 kilometers, 41.0 kilometers.
And do they give directions or not?
No.
They show arrows? Okay. The 27.0 kilometers, what direction is that pointed?
It's kind of like, it's north, but it's more north than east.
Okay. So it's east of north, but it's north and east, so it's sort of like this. Okay, great. And then the 41 is what direction?
That is south of east, I guess it would be.
Okay,
but
sort of like...
It is like, it's kind of halfway-ish. So it would be like a 45 degree.
Okay.
So it would be south of west then. Oh, yeah, south of west. Sorry.
Okay.
Back.
So, and did they give angles, by the way?
Yeah.
Okay, perfect. So what's the angle on the 27?
That does not have an angle.
Okay.
So we have O1, or degree 1 equals negative 35, and then degree 2 is 65.
Okay.
And so
maybe.
Yeah, you have your little guess grid is.
Oh, good. Let's draw a grid. We answer this one by drawing a grid, but it's good that they tell you to. Okay. And the first one is 27, and does it go? Is the angle sort of to the left of the vector or to the right of the vector? Well, you said it was east of north? Okay, so it's in here, sort of?
Yeah, that's our D that we don't know.
Oh, that you don't know?
Yeah.
Okay. All right.
And then kind of from the origin, you're going to go like in the negative, I guess that'd be the fourth quadrant, negative.
Okay.
It's kind of hard to explain. But like negative 45 degrees from the origin.
Okay.
So way in between that, and then from there you'd also go. I'm trying to make a triangle.
Yeah. Does it go here?
No.
Okay. Do you want me to go and make a right triangle sort of like this and like this?
It's like that. It's that, like, turned clockwise, I guess it would be. Like, 45-degree angle.
Okay. So, do you want to go to the, oh, you said fourth quadrant, excusez-moi.
Yeah, like that, and then connect that to that one.
Okay, do you want me to connect it all the way to the very tippy top?
The blue line is going to be turned a little more clockwise so that
I got
make an equilateral triangle.
I gotcha. Okay. So first we're going to go down sort of like this, right? And is theta above it or below it?
It's labeled, like that line is labeled D1, so that's 27.0 kilometers.
Okay, 27.0, very good. Goes straight up, doesn't it?
Kind of goes at an angle, kind of, because it doesn't have any right angles for this one.
Okay. All right.
So you triangle, and then...
And does it go like this?
Line, it goes inward.
It goes in, like this?
Yeah,
Silly?
so
okay.
On the right track.
Okay.
And so, is there a way I can send you a picture of it?
You do?
Or offer myself?
Yes. Hold on just a second. Hold on just a second, darling. I'm going to make you the presenter.
Okay.
All right. So now you've got access to the whiteboard. And what I want you to do is pick a color at the top, and then you see that fat magic marker? You need it, change it into a pencil. Like there's a drop-down menu, and you can change to get the pencil instead of the fat magic marker. Top.
Am I right here?
Yeah, your mouse. And do you see a whiteboard?
Yeah, I think. Yeah,
okay.
I'm on.
Yeah, perfect. Now pick a color and then change to the thin pencil because the thick one is too thick. So there's.
I'm not getting a drop-down bar.
You're not next to that pen, next to that magic marker. You're not getting it.
No.
Oh. Colors.
Yeah, black right now.
Okay. Well, sorry. Thickness. So you can, yeah, really fat, and we'll enjoy the fat black. Ooh, you switched to pencil.
All right, so grid, and then
okay.
mine goes like that. I don't know. And then the second one kind of goes down like that. And then
yes, I see.
That.
Okay, perfect. Hey, I like it. Well, can you make them vectors for me? Like make arrow tips on them. Okay.
And this one also goes up, so I'll just do like off to the side. And this one goes this way.
Okay, good. I got it.
Well, why can I not make it something with highlighter?
I don't know. Isn't that weird? So you see the little arrow next to it? You can't click on that and drop down and get the pencil?
I can't.
Strange. Okay, so now I get it, and I'm sorry it took me so long to get it. All right. So do you mind if I go back to my whiteboard and show you how to solve it?
No, go ahead.
Okay. I'll see if I know how to get back to my whiteboard. Hello. There. I should make myself the presenter again. That would help. The presenter. Share my desktop. We are back to me.
Alrighty, there we go.
Okay. I like it. Okay. I think I remember what you drew. I hope I did. So, I'm going to say I think I had this.
Yep.
And I think we had this maybe, and I think we had something that went straight up.
Yep.
Right?
Yeah, not straight up, but
it's okay.
Straight up.
Okay, I gotcha. So, is the top one a little bit longer?
Yep, they both meet at the same point.
Yeah, but it's sort of like this. Oops, that was not a very good one.
Yeah.
It's okay.
Yeah, that looks good.
It's pretty good. All right. So if the first one is 27.0 kilometers and the second is 41.
Yeah.
Okay.
No, 27. Yeah.
7 and 41, and then this one is the. And you know that it's resultant. Here's why. It goes very beginning, very end, and so that is the resultant. Okay, that's the answer. That's like the shortcut. And then, if you were walking in the woods and you went this way and then you went this way, you could have taken the shortcut and gone along the red resultant. That's what we're looking for. So here's how you do it. These are really cool. So we want to resolve or break down each component to the x and y components, or the x and y. I want to say components. Yeah, I should say each segment into the x and y components, but into the x and y amounts. But we're good. I'll just say the x and y. So, what do you see how if it's not a right triangle, they can't use sine, cosine, and tangent. So here's a special example. Say it's not a right triangle. So you can't use sine, cosine, and tangent. And like, oh no, what do I do?
Okay.
Okay? And so the way you're going to do it is you're going to have to sort of break it down separately. So watch this. I'm going to take the first one. The first one is this 27 here. Did they do an angle either like here or here?
Yeah, hold on. The first one that you did between the positive, I guess positive x side and negative.
Yes.
The first one one is negative 35 degrees. That one.
Okay, so this is 35 degrees right here. Okay, so what we're going to do is we're going to as a triangle over here. I'm going to say 27.0, and we're going to say this is your x component, and this is y component, and this is 35 degrees.
Yeah.
Okay, we're going to break this down to the x and y, then we're going to break down the other one into an x and y, and then to add the x's to the x's and the y's to the y's. So I'll just do it slowly. So here we have an x and y. We could do sine, cosine, and tangent with this x and the y. So I'm going to do is I'm going to say cosine of 35 equals the adjacent over the hypotenuse. So that's going to be x over 27.0. Say cosine of 35, or 20 times cosine of 35, and I get 22.1. So x is 22.1 kilometers. So far, so good?
Yep.
Now we get y. Y is going to be from the sine. So then we'll do sine of 35 equals y over 27.0. It's opposite over hypotenuse. I'm going to say 27 times sine of 35 in my calculator, and I'll get 15.5. Y is 15.5 kilometers. So far?
Yeah, we're good.
Okay, 22.1 is on this side, and 15.5 is on this side. I'm going to say, I'm going to make a little list, maybe up in the top left corner, and I'm going to say x1 is 22.1, and notice that the 22.1, check this out, is over to the right. The x to the right and the y is down. So x1 is 22.1 this way, kilometers, and 1 is 15.5 in the down direction. So we're making a list over here in the top left-hand corner. Now let's do the 41 guy. So I'm going to do it over here in this space. What color should I use, Hunter?
Orange.
Okay. Okay. On one, where did they give us an angle? Did they give us an angle anywhere?
41. No, 41 doesn't have an angle.
Give you a theta 2 or anything like that?
Yeah, see 5 degrees.
65 degrees go.
In the outside of B2, so outside of 41. So
it's like right here?
No.
Okay.
It is. You were 27 ends, that arrow right there.
Yeah.
It's right. It's that angle.
It's here.
It's outside of the triangle.
It's out of the triangle. Is it right?
Yeah. Yeah, it's that one.
It's this one right here?
Yeah.
It is.
That's
Okay.
65.
Okay, this one is 65 degrees. Oh, thank you. So we'll get this one and we'll get rid of that one. So what we need to do is we need to figure out, so 41 is at 65 degrees. This is very interesting. This was at 35 up here. 35 was in here. It's not showing up. 30. Do you see 35 that I drew really small? Okay, so 35 is in there, and 35 there. Let's see if we can figure this out.
So we can subtract 65 from 180 and get that other angle.
Okay, that sounds good. So
15.
1, very good.
Yeah.
So this one's 115.
And the one up top is 65 also.
That's 135. What's 1 and 35? 150. So maybe, oh, and the 35, sorry. You know, I don't think we know that the one up top is 65 because we don't have parallel lines anywhere.
Oh, you're right.
But we can say that with 5 and the 115, that's 50, right?
Yeah.
Do you agree? I'm going to choose the orange again. Would you agree that this right in here? Ready? I'm going to color it in orange. Or it's pink. Do you get the pink angle is 30 because the three of them have to equal 180?
Yeah.
Okay. So that one is 30. This one is also 30. That?
Yeah, because those are like reflexive angle.
Right. Okay, we've got a 30. So we figured out the angle for the 41, which took a little detective work, I think. We did a good job together, though. Okay, let's do this. Let me find a really fun blue. see what this blue looks like. So do for the 41, here we have 41.0. And yep, I didn't draw it at the right angle, but it's okay. It came up at 30 degrees from the x-axis. True?
Yeah.
Notice I drew my x-axis too far. But whenever you do that, make sure you don't worry. Just make sure that when you draw your triangle, you make it a right triangle. So it's okay that I drew one of them too far. Just cut it off. All right. So do you use triangle?
Yeah.
I do too. Now, the 41 is obviously at a weird angle. Whenever they give you something like a 41 that's sticking out at a weird angle, that's usually like 99% of the time going to be your hypotenuse, the one that's at a weird angle.
Okay.
It's going to be, and whenever they do give you a hypotenuse really quick, whenever they give you a hypotenuse, you're going to be drawing, okay, now I've got the horizontal part and the vertical part, and you make the two legs. That's just job. So whenever they give you something like, here's something weird angle, oh, okay, I can make the vertical and the horizontal. And by the way, it doesn't matter if you draw the angle above the arrow, or you could draw it below the arrow.
Okay.
Like, hey, you're going to get the same answers. Hang on while I just sort of make all that disappear with my little undo button. Oops, let me redo a couple things. Okay, so a triangle, and we made the weird thing that was sticking out at an angle, the 41.0, that was strange. We made that the hypotenuse. We got the horizontal, and we got the vertical. So would you agree that this is our x and this is our y? Okay, so yeah. So let's set the x and the y using sine, cosine, and tangent. I would say that the sine of 30 degrees is opposite over hypotenuse, so we're going to do y over 1.0. How do you like that?
Opposite. Yeah. Good.
So then we say 41.0 times sine of 30 is going to equal y. We're going to the calculator.
30. You got 0.5?
Me too. So x, and this x is cosine. Cosine of 30 equals adjacent over hypotenuse. Can I tell you the only way that I remember cosine?
What?
Do you see how the x is right up next to the angle? Right next to the 30? So when it's side, like one of the sides is right up, snuggling next to the angle like that, I say it's being cozy with the angle, and that's how I remember that's cosine. So cozy cosine is the one that's snuggling up next to the angle.
All right.
Okay, so 41 times cosine of 30, I get 5.5.
Yeah, with some change after that.
Yeah, with some change. 35.5 kilometers is our x. So now for this section, okay, this is like we're really breaking it down. Every time I answer, it feels like we're done, but we're not done yet. 30.5, and then the y was 20.5. And so now agree that we've got we're going to call this our x2 and our y2. So I'm going to go over to our list at the top left of the page, and I'm going to say x2 is 35.5. And I have to draw it. Teachers make mistakes. I forgot to draw it as a vector instead of just a line. So the 41.0, do you agree the 41.0 goes up and to the right?
Yeah.
So I want to make the x go to the right, like a vector. And I want to make the y go up because the 40 goes over the right and up. It's both up and over.
Okay.
So our x2 is to the right, 3.5 to the right. Our y2 in our left-hand corner is 20.5 up. only gave us 2 vectors to add and not like 17 in a row, but there's some problems where you have to do this like 5 times. But thank Lord, give us just 2 of them. What's it, 35? Look at that 3. It didn't show up very well. Okay, just gave us, so now all we have to do is add them. So what you do is you're not allowed to add an x to a y. You have to add the x's to the x's and the y's to the y's. So let's get a total x. If you don't mind, I'm going to use my special eraser and get rid of my little note, not right triangle, just because I need them right here, and can't use sine, cosine, and tangent because it's not a right triangle. I mean, you can use them, but you can't use it immediately. Okay. And I'll get rid of the sad face since we're starting to understand it, so we're feeling happy. So we're going to do total x and total y. Try a nice teal color. Total x. The total x. No. Hang on. The pen is saying it wants a new battery. So we just have to give it a new battery. 6 now. Okay. So we have a total x. So x's, we have 2.1 to the right, and we 35.5 to the right. And they're in the same direction. Does it make sense to you that we're going to add those numbers because it's like they're both positive?
Yeah, both going the same way.
Mm-hmm. And you can say to the right or you could say positive. It's like positive 22.1 and positive 35.5. I got 57.6 to the right. Okay, that's our total x. Now do a total y. Why is my pen doing this? Okay. The y is 15.5 down. And the second one is 20.5 up.
Subtract those.
Yeah, here's where it gets handy. Instead of the down, we're going to say negative. And instead of up, we're going to say positive. Because in physics, negative and positive just mean direction. So down, to say down is negative and up is positive. So 0.0. And is down? Up because it's positive. Exactly. You wouldn't, in a real test, you don't want to say positive and up because that's being redundant. So you would either say positive 5.0 kilometers or you'd say 5.0 kilometers up. So since I added the positives and the negatives, I'm going to erase the little arrows because I technically don't want to have both there. All right. So see how we have, I'm going to use yellow, we have a total x, we have a total y. We're going to take the total x and the total y, and we're going to make what I like to call a final triangle, where the x and the y. I know this is a lot of work for one problem, but that's how it goes. It's like it takes a whole page to do one problem. All right, you think of a color I haven't used yet. I think red would clash.
Yeah.
I could use like an amber.
Okay.
All right, let me try an amber. Okay, so in the middle, even though there's not much room, I'm going to do the final triangle. It's supposed to be amber. It looks brown. Final triangle is your total x and your total y. So the x is 57.6, which goes like this. and your total y is 5.0. Oops, I shouldn't have done the 57.6 on top. I'm going to need, okay, 57.6 goes here, and then 0.0 goes up like that. So here's the final triangle, and the resultant is going to be that. So now we have a simple right triangle. At the beginning of the problem, we did not have a right triangle. To break down, get the x's and the y's, we had to add all the x's, we had to add all the y's so that we had one x and one y. And once you have one x and y, like a total x and a total y, then you can make one simple right triangle with simple normal sine, cosine, tangent.
Okay.
Okay, so now we've got a resultant, and we can figure it out using, first let's use Pythagorean, shall we?
Sounds good.
Okay. So I'm going to do a squared plus b squared equals c squared. And we're going to figure out this by doing 5 squared plus 57.6 squared square root 57.8.
Yep.
Okay. 57.8 also. That is kilometers. If for just the magnitude, we would be done. However, they probably said find the magnitude and the direction of the resultant. So I have to find the direction. I do have to find the angle that is in here. So I'm going to call theta, even though we keep using theta. We'll use it again. So you see the opposite and the adjacent? Let's use tangent. So let's say tangent of theta, which we don't know, is it, which is 5.0. Adjacent.
57.6.
Mm-hmm. So I'm just going to do 5.0 divided by 57.6, and I get 0.0868. And so we flip sides and we say inverse tangent of 0.0868 equals theta. And I get 4.96. I feel like our answer doesn't exactly match the picture.
It's pretty accurate.
Really? Because 5 degrees, so we just figured out as theta is 5 degrees, which means this in here, like 4.96, that means this is basically 5 degrees in here. I don't know. I don't think we made a mistake. It's right. So we could say 57.8 kilometers at, let's give direction, answer. And right now I'm writing in the middle of the page right above the word U on You Really Do Love Science. So we're at 4.96 degrees. And would you say the degrees could say from horizontal or from the x-axis? Does it show x and y-axis?
Yeah.
So in this problem, it does say x and y? Okay, so then we want to use the same language that they used in the original problem. So we'll say 4.96 degrees from the x-axis. And C is just from the Pythagorean theorem. I'm actually going to call it R for resultant. So this would be the answer, and that magnitude and the direction.
We got it.
We got it. To break down, since it wasn't originally a right triangle, we have to take the parts, we make each part into a right triangle, so we have to get the x and y of those separate triangles. Once we have the first x and y and the second x and y, we add those, we got our total x and y, and we made what I call the final triangle. And the final triangle is simple with sine, cosine, tangent, and that gives you your resultant.
All right.
Like it?
Yep.
Okay. So this is just some example problems of